All right, so today, this is session 2, biological agents decontamination. I have the pleasure of moderating this and introducing our first speaker, whom I've gotten to know over the last few years. It's Ahsan Ghazi. He's a principal scientist in CBR hazard management at the UK's Defence Science and Technology Laboratory. That's DSTL for everyone. And he's a chartered chemist with the Royal Society of Chemistry. So we're amongst royalty here. He attained his PhD in chemistry from the University of Manchester in 2004, where he worked on imaging of tumor cells classifying disease states of cancer. But in 2010, he joined the CBR hazard management team at DSTL, where he developed analytical methods and empirical models to determine the mass transport of chemical warfare agents in porous materials. And then in 2013, he started working on something that's dear to my heart, defense provision and logistics for viable methods of decontaminating wide areas of Bacillus anthracis using agricultural approaches. So I'll turn it over to Ahsan.
Thank you, Worth, for the introduction. I'm going to be talking today about logistically viable approaches for wide area decon of Bacillus anthracis using surrogate spores. So what I'd like to do is start off by outlining the challenge. So we know that Bacillus anthracis is the causative agent of the fatal disease anthrax, and it's an important threat agent of concern because it's very persistent in the environment and very resistant to chemical decontaminants. And in fact, this has been exemplified by some real-world examples. So Grignard Island in the 1940s, the War Office actually disseminated biological spores onto this island. And that was sort of an attempt to understand the hazards associated with that type of release. And 40 years later, soil samples were actually taken by Porton Down scientists. It was actually found that there were still spores persisting in those samples. And a huge logistical effort was performed in order to decontaminate that land, which involved burning away the vegetation before 500,000 litres per hectare of formaldehyde, very harmful chemical, was used to decontaminate it. So essentially irrigating the land with a very harmful chemical. The Amerithex incident, 2001, attacked through the US postal system. Some buildings weren't actually reopened until 6 years later, and the cost of remediation went up to hundreds of millions of dollars. And actually, we can regard that as a relatively small event compared to a potential wide area release of anthrax over a wide urban environment, which would have much greater consequences in terms of human health, the environment, economy, and essential services. So what we're doing under this anti-agar program is to develop logistically viable, cost-effective, rapid methods of decontaminating wide areas. And this is all predicated on low-volume strategies. And that involves 3 things: decontaminant formulation chemistry, spray technologies, and collecting dose response data. And it's that strategy which is actually best practice in the agricultural industry to efficiently apply pesticides over hectare-scale areas of crops. So what we're doing essentially is taking that strategy and adapting it to our defense needs. So if we look at these in a little bit more detail, regarding decontaminant formulation chemistry, if we consider some spores on a porous surface, the aim of developing an effective decontaminant is to maximize the contact time between the active substance in the decontaminant and the target spore. And this can be done by adding chemical adjuvants into the formulation. So, for example, we can add surface wetting agents in order to ensure that the surface is suitably covered so that all spores on the surface are in contact with the agent, incredibly important, which is very different from agricultural purposes where discrete drops on a leaf can have an effect. We need complete surface coverage. We can actually use rheology modifiers in order to be able to retain the formulation at the locality of the spores on the surface of materials without it significantly absorbing into porous materials, again, for the effect of maintaining the contact. And again, in a similar vein, we can use humectants in order to reduce evaporation rates so that, again, we extend that contact time between the active substance and the target spore. Regarding spray technologies, it's really important that the decontaminant that we develop is compatible with the spray equipment. And it's really important that we understand any risks early on with regards to compatibility. For example, using surfactants in formulations can cause excessive foaming. And that can actually depressurize the lines, and therefore you can actually deliver a lower dose than expected to a surface. But we have ways of mitigating that using silicone-based anthophones. In a similar way, if the formulation is too viscous, we need appropriate pumps in order to deliver the right flow rate, the right delivery of the target dose to the surface. And also incredibly important is that the decontaminant, if it's an oxidative corrosive decontaminant, is compatible with the materials used to build the spray equipment in order to ensure we've got longevity in that equipment. Regarding collecting dose response data, what this is really a systematic way of being able to relate the concentration of the active substance in the formulation with the spray volume applied and the hazard log reduction achieved on a surface, whether it's porous or non-porous. And analysis of this kind of data sets allows us to identify the minimum applied volume we need to apply to a surface in order to maintain a contact time, which is effective. And this is really important because it reduces wastage. We don't want to apply more than we need in order to affect a target level of kill, because you have to remember, for every liter excess per meter squared, it can result in 10,000 liters over just 1 hectare. So I looked up the US sort of conversion here, and that would work out to be 2,600 gallons across 2 NFL football pitches. So I'm hoping that sort of gives some context to it. And I just want to point out that we recently published dose response analysis of formaldehyde, a well-known sporicide, for decontaminating spores on a range of representative urban surfaces, and collecting very comprehensive dose response information in respect to that. Regarding our technical strategy, essentially what we do is start in the laboratory using high throughput methods in order to optimize formulation chemistry and spray delivery protocols. And then once we've actually identified the most promising combinations for hazard reduction on inoculated surfaces, we take that forward to wind tunnel applications, where we work with Silso spray application units who are experts in agricultural spray delivery. And we're able to deliver our decontaminant onto inoculated surfaces at the doses, at certain target doses. You can then take those treated coupons and put them in the environment chamber in order to understand the efficacy of that decontaminant under controlled meteorological conditions. And that's a really important factor for real world translation. And once we have that data, it informs our trial design, where we upscale the amount of decontaminant we produce, the delivery method using vehicle-borne spray systems, and we really get a good understanding about the logistics involved in order to decontaminate contaminated surfaces. And throughout that whole process, we use the same strain, Bacillus thuringiensis H2.1 cry negative, which is a safe hazard group 1 organism for virulent Bacillus anthracis. And this was developed at DSTL, so it's lost its parasporal crystals, so it's non-insecticidal, so can be used in the outdoor test range because it doesn't affect the local ecology. It's comparable both genomically and phenotypically with virulent Bacillus anthracis, and it has exsporium coating. So over the next few slides, I'm going to talk about a concept demonstrator that we developed for wide area urban remediation. Our aim here is to develop a practical decon system that achieves 4 log CFU per centimeter squared kill, or 6 log CFU per centimeter squared kill on a range of different representative urban materials, going from impermeable steel to wood, asphalt, brick, and limestone. And we inoculate these surfaces by using a medical nebulizer in order to perform aerosol deposition. There's some glass slide photomicrographs there that you can see about to show you the spore distribution. If you want to learn more about the mechanism, it's in that reference, just in red font at the bottom there. We want to be able to decontaminate surfaces both on horizontal and vertical orientations using less than 0.3 liters per meter squared of formulation. So essentially less than the amount contained in a Coke bottle over a meter squared. So this slide sort of shows our bespoke spray system that we've used in full-scale trials. Essentially what it is a skid chassis, so a metal pallet, on board which we have put a 60-litre MDPE tank. So it's a medium density polyethylene tank, so it's resistant to oxidative decontaminants and corrosive decontaminants. We have 3 diaphragm pumps and 3 electric batteries in order to deliver the formulation into a 3-meter boom, which is equipped with 15 agricultural nozzles. And we use different nozzles depending on whether we're spraying to ground or to a vertical surface. Oh, I should also say the boom itself can be hinged at 1.5 meters, so we can actually spray up to around about 2 meters above ground. In regards to the decontaminant formulation, we're using a peracetic acid-based formulation, which is a very effective sporicide. Essentially, peracetic acid exists in equilibrium with hydrogen peroxide and acetic acid. We adjust the pH to weakly acidic to neutral conditions, so it's much more material compatible with spray systems. We know, however, that above pH 5.5, peracetic acid anion is produced, which reacts with the peracetic acid molecule to actually cause greater rate of decomposition. So understanding the pot life of peracetic acid formulations when pH adjusted is important. We have 2 formulations that we've tested. The first one, called F004AT2, was tested for ground application. Essentially, a formulation is just quickly shown there. Essentially, it's 3-part formulation. The first part is a buffer. Second part is peracetic acid at final dilution of 5%. And part C, a nominal dilution at 5%. And part C is sympyronic, which is a surfactant. You can see the concentration profile there taken using a potentiometric method or peracetic acid concentration determination. You can see that at T0, essentially by adjusting the pH to around about 67, we get an initial drop from a nominal dilution of 5% down to around about 3.5 to 4%. It's also important to note that actually we use local tap water. So Porton tap water is actually very hard. It has something like 226 part per million, mainly of calcium and magnesium. And when we actually make up the buffer component, calcium and magnesium produce partially insoluble species of calcium hydroxide, magnesium hydroxide. And these we found in our full-scale system testing to actually affect spray equipment. It actually causes blockages in some of the nozzles. So in our next formulation, which was for vertical surface application, essentially what we've done is replace the local tap water with reverse osmosis water or demineralized water. This is a 4-part formulation for vertical surface application called F015AT. So it consists of the buffer with Kelzan. Kelzan is a rheology modifier. It's basically xanthan gum. It contains peracetic acid, a silicone-based antifoam, and a surfactant. Again, the nominal dilution of the peracetic acid is 5%. And as you can see in the peracetic acid concentration profile there, in fact, with the addition of Kelzan, we're getting much more stable dilutions at T0 of around about 4.8 to 5%. The initial pH was at pH 6. So moving on to the trial site, this is a slide just to show some basic information with regards to that. Essentially, we used a Porton range, the OP6 barn, which essentially is a 60-meter length, 10-meter width, semi-enclosed environment with 2 huge doors on each end that allow some equilibration with the outdoor environment. It's important to note in the barn, when we do our decon tests, there's no solar radiation. As you can see in the bottom right sort of aerial photo there, the spray track is in the middle. And on one end, we have the decontamination preparation and spray loading area. And on the other end, we have the positive and negative controls. So the positive controls are essentially inoculated surfaces, which are taken from the lab and placed in that area, not decon treated. And that enables us to understand the effect of the environment alone on spore viability during the decontamination experiments. The negative controls are essentially blank coupons in order to understand any background flora that may affect downstream analysis. And so we have those 2 controls. Regards to the spray track for ground application, essentially what that comprises is pallets which are laid out on the ground. We have a 9-meter spray track, and on those we have gauzes on which we put our inoculated coupons. We also have Petri dishes which are pre-weighed. So when we actually spray in those inoculated surfaces, we're also collecting the volume that we onto the Petri dishes so that we can weigh them after in order to work out what the volume of deposition was on the actual surfaces. And you can see in that sort of heat map there, essentially we can get a really good understanding about the reproducibility, uniformity, and variance around actually depositing the target volume across the spray track and across the 9-meter spray track, or essentially across the width. For vertical surfaces, this is a little bit more different. Essentially, what we've had to do is develop a 3D printed cassette. And on that, we put our inoculated coupon, which is a target area we want to spray using our vertical orientated boom. And below that, we put a blank coupon. Now, the reason for doing that is because once the decon has been sprayed, we want the decon to run off like it normally does on a larger uniform surface. And a blank coupon enables that. Otherwise, what would happen is that if we had just an inoculated coupon on its own, we'll get edge effects, essentially accumulation of the decon at the bottom end of that, and that can artificially increase the performance of our decon, so we don't want that. In the same way, above the plane of the inoculated coupon, it's a gauze. So any of the overspray from above the plane doesn't actually run down to replenish decon lost as it's been run off. So essentially what we have is a very conservative result in terms of decon performance from this system. So each of those cassettes, and we have many of those across the fences there, these are harassed fences. So we mount them basically with pins so that we can easily mount them for spray application. The other thing that we do is actually apply pre-weighed filter paper. So in the same way we're trying to measure the volume deposited on the ground using Petri dishes, this time we're using filter paper, which is pre-weighed. We have 3 aligned with essentially each of the nozzles on the spray boom. So A2 there is in line with the inoculated coupon. And again, we're able, after spray application, measure those filter papers in order to work out the volume applied and the consistency of that application across the fences and also across the vertical plane of the spray boom. So just to recap in terms of our procedure, we do our decon preparation on board a pickup truck holding our bespoke agile spray system. We take a sample for characterization of the prussic acid content in a field lab. We spray the decon, whether that's vertical or ground application, onto our coupons, and we take the filter paper or the Petri dish for understanding what the volume of deposition is. And when you combine the volume with the dose, the prussic acid determined, we can actually work out the actual dose applied to the surface. The coupons are collected after 2-hour dwell time, and they're collected into falcon tubes that contain a quench, sodium bisulfite. We also have sand in those falcon tubes, and the reason for that is because in order to recover the spores from the surface into the suspension, we have to vortex it. That sand then abrades across the surface, immobilizes the spores off into the solution, and we're able to take an aliquot for serial dilution and standard TSA plate culture for enumeration. And this is just some example of data that we got for ground application. Essentially, each of these graphs, we have BT log reduction on the y-axis against increasing dose on the x-axis there. So on the top left, we have steel data. The initial inoculum, essentially 7 log, and we can see that we're achieving really good levels of kill of greater than 5 log or above using our approach, using essentially 1/3 of a can of Coke per meter squared. On the more absorbent surfaces, we're getting lower levels of hazard reduction as we would expect. So the lowest there is wood, and we think that's because prussic acid interacts with organic material and therefore is quenched because of that, and so there's less availability for spore interaction. And asphalt and brick are sort of in between. Regarding vertical application, we get very similar results. Essentially steel, this, by the way, this is showing obviously box plots, which show a better idea about the spread of the data. So we can see on steel, we're getting, again, pretty good performance of greater than 5 log generally and above. But with the more absorbent materials, we're getting reduced efficacy. But this is after one application and a 2-hour contact time. But this at least baselines the performance with regards to the decontaminants and spray application. It's very important that we correlate our results that we get with our hazard group 1 simulant, Bt cry negative, with virulent Bacillus anthracis AIMS, and we can do that at containment level 3 in suspension tests. So here what we're showing is spore log count against applying 0.5% protic acid, either adjusted with pH adjustment to pH 6 or non-adjusted at 2 different time frames of 5 minutes and 15 minutes. And we can see that Bacillus thuringiensis, HA1 cry negative, is much more hardier than Bacillus anthracis AIMS. Again, really good because we want to be on that side of the fence when we develop our Decon system using this surrogate strain. So I'm really glad that that's the case. So just some key messages to round up. Essentially, methods, equipment, and processes have been developed by our team to test and evaluate systems for full-scale decontamination of represented urban surfaces. This identifies any issues with regards and risks with regards to Decon application using our sprayer system. We have baseline data now on hazard reduction achieved using our low-volume approach by surface type and meteorological parameters. And the dose response data at full scale essentially validates subsets of a larger data set that we have at laboratory scale. And this is really important for potential operational support and reach back. And ultimately, we're doing all this to de-risk technical and logistical issues for end users. So it just remains me to thank everybody that's contributed to this project. So thank you so much for listening and happy to answer any questions.
Questions for Ehsan? I'll ask a question.
Oh, no.
Hold on, I'll come back. I saw a hand. So a lot of good work has gone into optimization of your spray system, the delivery system, the chemistry. Have you thought how that is going to play out for the real world when you have 3D structures like grassy fields or other wind in your spray conditions?
Yeah, that's a really good point. In the real world, there's many, many factors. And I suppose what we're doing is starting with a simple system. You know, we've got flat surfaces. We're trying to get a really good understanding, a baseline of dose response on flat, clean surfaces under no wind conditions, ideal environment. And essentially in the portfolio work going forward, we need to start building up the complexity again in a systematic baby step way. But we have, you know, for example, wind, seal-safe spray application units have a wind tunnel. And so we're able to, you know, start to understand what the effect of those kind of conditions going from gentle wind or 0.5 meters per second, for example, has on the spray drift, for example, when we're applying using our particular decontaminant. The other things are, you know, the agricultural nozzles themselves, you know, if there is a change, you can change obviously a droplet size to counteract that. So there's a huge piece of work with regards to each of those parameters going forward.
Steve Sandrowski, EPA CMAT. I was wondering if you had accounted for or assessed the physical removal of the spores during your spray trials. So, for example, the spores may just be sticking to the wood better than to the other surfaces. Thank you.
Yeah, so a really important control in our studies are essentially a blank liquid spray. So we apply the formulation without the active substance. So essentially it's water, the rheological modifier, surfactant for the more complex formulation, sprayed onto the surface in exactly the way we typically do with the Decon in it. just to understand if there's any differences compared to population controls, i.e. non-treated, just nebulized. And from those results, we can see that there's no sputtering or mobilization of spores as a result of that. So yeah, it's a really good question as a control. Yeah.
Thanks, Asan.
Oh.